What's wrong? So in the second lab, we change the frequency and it's not change the speed of the wave because we know that. What does this symbol stand for? What does that symbol stand for? That's the wavelength. That's the wavelength. What's that measured in? And what's this T stand for, you think? Period, which is the measurement of time for one cycle. Period. And then what's our general equation for constant speed? Well, I'm looking for distance over time. Over time. And so what's our distance type term for waves? And our time is the period. So that's our equation for speed. We also know that frequency equals the inverse of the period, correct? We learned that yesterday a little bit. If we had a period of 2 seconds, and we had half a wave every second go past us, and vice versa. So this equation, this is what Jessica was kind of saying, could be changed to lambda f, wavelength times frequency. And so what happens in the second lab is that you increase the frequency of the wave, and that made, you saw, the wavelength got smaller, right? When we did that? Yeah. That decreased the wavelength, and those two things should change proportionally, such that the speed of the wave should always stay the same. Again, think back to light. Red light and blue light have different wavelengths. They travel at the same speed. They have, or excuse me, I should say, they have different frequencies. They travel at the same speed, so the wavelength must be changing. Changing the frequency of the light didn't change the speed of it. Same thing with sound. This is apparently an A note. It has a frequency of 440. It travels at a certain speed. If I had another note with the same thing, different frequency, they travel at the same speed also. So changing the frequency should not affect the speed. Questions? That was awesome. Okay, and the last one, none of you got to, and that's fine. You would have found that the force, the tension in the slinky, if you increase that tension, you'd have a faster speed for the wave. This would be kind of analogous, not exactly though, to if you are trying to send water through, or sound through air versus water or some other more dense material, it's going to go faster. So this is why, for example, and please don't do this because I worry someone can get hurt. If you were to put your ear next to a railroad track, you would hear the train before you hear it with your ear through the air. But again, please don't do that, or we're going to fall asleep and run over and get in trouble. So that's not something you should try, but it's true. And that's why, they talk about how Native Americans and cowboys should listen to the ground in order to hear their horses from further away than they're standing up and listening. So the more dense the material is, the faster the sound travels through it. Now it gets a little bit distorted, like underwater, sound is slightly distorted. And so that density has a downside to it, but you get more distance. If you speak whale or something, you speak in the water and it'll go further than if you're speaking in the air. That's why whales have to really do. That was too much. Didn't make any sense. So in terms of what you want to get out of that lab, as long as you have those equations written down, and you can kind of figure out the relationships, so we know that the speed of a wave could be either lambda over period or lambda times frequency, and that frequency is the inverse of the period. You're going to be able to figure out anything else you want to know. In a certain medium, the speed is never going to change. All the sound waves going through air are going to be the same speed. This better be true, because again, if you were at a concert and the A notes travel faster than the C notes, that would be problematic for you, right? Because if you're trying to make a chord and the C note is traveling through here before the A note, and the C note's not, the A is left over, it would be very awkward. And so in the same medium, the same kind of wave always travels the same speed, similar to back in the string we had yesterday. And if I change, what's wrong, Jessica?
Why is something sensitive of the faster velocity really bigger than the opposite?
Why would you?
Because it's such bigger intense, and then that travels faster.
The particles are closer together. So, like if you have, why would you think it would go slower?
I'm just thinking what if I taller, it's sensor, so maybe it goes slower. Is it guided more?
They go slower. Yeah. Because they can't speed up as much while they're falling. You have to trust me. I used to laugh because of that. Because if you put them right by each other, they don't, gravity not pulling them as long, so they can never speed up. If they're further apart, they can speed up longer. They don't like accelerate while they're going, but if they're further apart, they'll go further. Why is a wave different than a Hoyle flow of people? Yes, this is. I know that what I said is correct, so I'm trying to think about why. Yeah. Yeah, you don't want to think about the particle individually moving. You're thinking about the energy traveling through the group.
Oh, so if everyone's closer together, it's easier to get it through everyone.
Yeah, kind of. If you're playing operator, it's going to be easier if you're all next to each other than if you're way far apart from each other.
Makes sense. Guess what? Cystic fibrosis 1.
But anyways, so this wave right here is one of my nice fun standing waves. There's a go. Come on now. There's one. You're going to move back when you're right there. Sure, I need spare time. So this standing wave is a frequency of 37.5 hertz. It's sending out a wave at a certain speed. If I increase this frequency to the next thing, find me where to go. Where to go? Then this is 73.9, yeah. And so now I have 3 nodes, but so I have a shorter wavelength, faster frequency. If I measure these wavelengths and did the math, I should get the same speed going through this string in different times. So that's kind of just showing that point. That in a certain medium, a certain kind of wave, what was at the same speed. And that's going to have some interesting consequences for us when we get to the end of class. Good. Questions so far? Anything else that we have to go over? I think that's all the questions that are important. So we're going to attempt today to do the impossible. Not yet. We're going to try. No, see it. Thank you. We're going to try to measure the speed of sound. So what we're going to do is we're going to take a tuning fork, which produces what? Sound. An A note in this case. 440 hertz. We didn't say that. The unit of frequency typically, we say is 1 over T. We could say it's 1 over a second, or we call that hertz. Like the rental car company. Names for some guy. I don't know if they're related to the same guy or not, but they're spelled the same way. Often abbreviated. The hourglass move. What are you doing? It did just freak out. Well, it should be HC. If you can imagine HC, there would be the abbreviation. So what we're going to do, we're going to take our tuning forks, which produce what? Sound. The A note, in this case, the A note, it says it's 440 hertz. There's a frequency of 440. Let's see that. We're going to whack it. We're going to hold over this tube. This is a cylinder with water in it with a glass tube inside the water. We're going to whack our note, hold it over here. We're going to raise up this tube. Whoa, there's a point where it's really loud, and then quiet again. And not loud again. There's a loud point. So there's one spot where it always gets really loud. And so I wonder why that is. I wonder if I can use that to figure something out. And so why do you think it's being loud at that one spot? Why is it quiet and it's really loud at one spot? What? Which one of the two?
I think there is another, but it's another.
A major one as opposed to a minor one?
The biggest one. Yeah, we're talking.
So there's my glass cylinder. There's some water. There's a plastic cylinder. There's the water. And then here's our glass cylinder. at that. And so now